Next slide. Gravity is what keeps satellites in orbit around the Earth. The animation shows that the orbital velocity is always perpendicular to the orbit. The direction of the gravitational force, and the acceleration, is always directly toward the center of the planet. The resulting curved path is a compromise of sorts between the two directions. Remember that the force causes a change in the orbital velocity. If the gravity force was turned off, then the satellite would move in the direction of the orbital velocity. If you are comparing the orbit speed or orbit period or time of two objects orbiting the same central object, for example, two planets orbiting the Sun, then their orbit speed and orbit period depend only on the size of their orbits. In Kepler's third law, the orbit period, time, increases faster than the distance changes. One planet or asteroid with an orbit twice as big as another planet or asteroid will take more than twice as long. An orbit 3 times the size of another orbit will have an orbit period of more than 3 times the other orbit. In fact, it would be 3 to power 1.5 equals 5.2 times as long. Next slide. The last general application of gravity we'll look at is tides. Tides are produced by different strengths of gravity acting on an object. A round planet near a massive moon feels gravity pulls of different amounts on it. These are indicated by the length of the red arrows that appear in one frame of the animation. The near side of the planet feels more gravity from the moon than the center of the planet, which feels more than the far side of the planet. The tides stretch the planet. Gravity works both ways, so the moon gets stretched as well. The solid part of the planet doesn't stretch as much as the water part, so we notice the ocean tides a lot more than the solid land tides. Notice that there are two tidal bulges created, one on the near side and one on the far side. The one on the far side is due to the far side being accelerated by the least amount, so relative to the center of the planet, the far side is moving away from the center of the planet. Tides are due to differential strengths of gravity. The tidal bulge is always aligned toward the gravity source, so as the Earth spins, the Earth's rotation will carry your part of the Earth into the tidal bulge and then out of it. 2 high tides and 2 low tides. Each moon phase produces 2 bulges. The moon moves in its orbit in the same direction that the Earth spins, counterclockwise. Therefore, the tides are more than 12 hours apart. The Sun also causes tides on the Earth as well. Even though the Sun's gravity is much stronger than the Moon's gravity, the differences in the Sun's gravity on the near side of the Earth facing the Sun compared to the side facing away from the Sun is about half as strong as the gravity differences from the Moon. The Sun's tides are half as strong as the Moon's tides. For any moon phase, you will experience high tide when the moon is on your meridian and about 12 hours later. The animation shows the times for the 4 major phases: new, first quarter, full, and third quarter. At new moon and midnight, the moon and sun work together to produce particularly strong tides called spring tides because the very high tide really springs up from the very low tide. The high tides happen at noon and midnight. At first and third quarter moon phase, the tides are really weak and are called neap tides. The high tides happen at sunrise and sunset. Much longer term effects of tides are the slowing down of the Earth's spin and the moon spiraling outward. I said a couple of minutes ago that the tidal bulge is always aligned toward the gravity source. Well, the Earth is spinning pretty fast, and the rock and water don't respond instantly, so the bulge is a little ahead of the moon. The moon's gravity tries to bring the bulge back into perfect alignment, so the moon puts a brake on the Earth's rotation. At the same time, the Earth's tidal bulge pulls on the moon, trying to pull it faster in its orbit. The moon responds by moving outward. These effects are pretty subtle. The sidereal day is getting longer by about 0.0016 seconds every century, and the moon is moving outward at a rate of 3 centimeters every year. When the moon formed 4.5 billion years ago, the Earth was spinning at about 6 hours per day, and the moon was only 40,000 miles away. The tides on the Earth were huge. Solid rock rose and fell by 200 feet every day. Similar sorts of tidal stretching and spin breaking occur in other places of the solar system and galaxy.